I
we gotta leave a couple just in case, that'd be kinda fun.
I'd enjoy that.
Those are like yours. You provided Mr. Williams.
He wins the prize.
He gets to give some points.
Okay, so where we left off, now remember we had the wrong derivative for our second derivative. I've cut and pasted the correct derivative, which means we have to go back
Are
and
you
fix a
recording?
couple things here, right? So
Are
we
you
had,
recording?
are you recording? I am recording, yes. So these were wrong, weren't they? Yes. Because there were no first derivative critical numbers, there were only second derivative.
There's only one.
There's only one, right. So we get rid of all this stuff.
One.
Okay, and then the picture's all screwed up, we'll fix that later.
That part's out.
That part might be okay, yeah. And that point was right. It's just maybe the rest of this isn't right. Okay, so then did we figure out, so here's our second derivative. We know we want to find the zeros of the second derivative. So if we just took the zeros of this function right here, did we figure out what they were? And we're going to cheat and do this using technology. One point something? Jenna's got it here.
I have the graph.
Okay, just go to, find the, we'll just cheat, find the, you have the graph of the second derivative?
Yes.
Okay, just find the zero of that.
It is 0.009.
Okay. So pretty close to zero. And the y was, what did we get for the y was 0 plus, right? Or actually, if we plug that in, what are we going to get for our function? That'll be easy to do. We're going to get something like about 1/10-ish, right? Okay, so it's like small positive. So we have our point in the correct place, we just need to know what it is. So if this is a zero of the second derivative, we'll just check points to the left and the right of that. So if we were to check values like -2 and +2, we just got to check the sign of those. And we don't have it factored, so that's hard to do. But if we were to take this function and evaluate it at -2, but what are we going to get? Do I need to type it in, or can you guys type it? F double prime of -2 is
It is positive.
positive. Okay. F double prime of +2 is negative. Okay, so then, so this is an inflection point then, isn't it? We're going from positive to negative. So it's an inflection point. And now we know we're going from concave up to concave down. So this part was probably pretty accurate.
Yeah.
We're doing something like that without a horizontal tangent because there's no zeros of the first derivative. Then all we have to do now over here is we're just going to check. We've got we've got this function that's coordinate off. It's got like 3 separate intervals, exists in 3 separate universes. So we got to check everything to the other sides of those walls, right? The vertical asymptotes. So if we were to check a value up here at like 10, and down here at like -10, what are we going to get?
10 is positive,
-10,
negative.
negative. Okay, so then what's that going to mean? If I know that it's got these asymptotes, it's got no extrema. These are the asymptotes that guide our behavior, and it's positive concavity. What's it have to do? Yeah, good, it's gotta do this, doesn't it? Right? Over here, if it's negative, what's it have to do? Yeah. It's gonna look like that. So this function, does it have symmetry based on the graph? No, it doesn't quite, does it? How come? That point's not at the origin, right? So it doesn't have that rotational symmetry. So if we were to check our test for symmetry, we should find that this thing doesn't have symmetry, and we would find that. Okay, how come? Let's just talk about that for a second. The function, if we look at the numerator, does it have even or odd symmetry? Actually, it has neither. Okay, here's how you can tell. This is kind of a good thing to talk about. And the bottom has neither. What's our test for symmetry? Even symmetry means f of negative x equals f of x, right? So let's just take the top, for example. I'll just take a picture of this whole thing. So if we take, let's just let the top, okay? So g of negative x equals negative x minus 3, right? That is, that is not equal to g of x, and it's not equal to negative g of x. Done. Game over already, right? Because both the top and the bottom would have to have some kind of consistent symmetry for this thing to be even or odd. Okay, the bottom, but I can tell that without even doing any math. Here's how you can tell. Where do the words even and the names even and odd come in? Why do we call them even and odd symmetry? It seems weird, right? Because there's nothing really even or odd about reflective or rotational symmetry. Exponents. Yeah, look. What are the exponents? I get x to the 1 minus 3x to the 0, right? Well, 0 is even and 1 is odd. If you have a mixture of the two, you have neither, right? If all of the exponents in a polynomial, and we always, the even and odd refer to polynomials. How come? Because we use polynomials all the time, right? And they're easy to check. Down here, same thing. I get a mixture of even and odd, okay? So I know right away it's got no symmetry. Polynomials are easy to check. So how would I do a rational function, though, and use this same trick? You're going to know this just intuitively. Say I had a rational function where the top polynomial was even and the bottom was even. What's the overall symmetry going to be? Even, yes. What if the top was odd and the bottom was odd? Even. Exactly, it's going to be even. What if the top, and can you see why that is? If you think about what the meaning of even and odd is, if even symmetry is f of negative x equals f of x, and odd symmetry is f of negative x equals negative f of x, it's essentially following the sine rules, isn't it? Right? If both the top and the bottom were odd, well then negative over negative is going to be positive, right? If they're both even, obviously it's even. What if there's a mixture of even and odd?
Then it's odd.
Then it's odd. Right? Everybody see that? Okay, so there's a really quick way to diagnose symmetry for rational functions. I don't think that even really comes up in the textbooks, but it's kind of a cool thing to just to know. I mean, there's a nice little way you can look at the even and the odd. It's pretty easy to do quickly. Yeah, we're done with that one, okay? Oh man, there was a reason I wanted to do this one. We'll just keep chipping away. So I know you probably, like in this class, there are certain things that we seem to get stuck on, and we spend a lot of time on, right? this is one of them that I think is really important, because it brings so many things together. So we're gonna, I mean, I'll probably, I don't wanna do too much in any one day, but we'll probably kinda stick with this for just a little bit, maybe do at least another day after today, even of going through some of these problems, just so you've seen how to do all of these different, I'm gonna pick all the kind of main ones, so you can see how to analyze those using a table. Just, and even if you don't completely get it this year, I mean, it's gonna stick in there, right? You know the way the brain works, if you can create some prior learning, it's easy to relearn stuff, even if you don't retain all of that stuff. If you've seen it before, in the future, you'll be able to kind of easily recapture that, right? Okay, so let's look at one more of these rational ones. This is an easy one to do though, right? It's easier to do, smaller rational function. So what's our domain here?
X can't be.
Can't be 3, right? Are there any zeros at the top? No. Agreed? Top is nowhere 0, but the bottom is 0 at 3. So x cannot equal 3, and what's that going to give us? Vertical asymptote or hole? Vertical asymptote. Unique 0 at the bottom is a vertical asymptote. So right away, let's do our, I don't know, let's do our derivatives real quick so I know where to put the table. We'll come back to that. These are easy to do. Let's use quotient rule. So what are we going to get? Times 2 minus
X squared.
times 1 all over x minus 3 squared. So these are pretty easy. If I just distribute on the top, there's nothing really to factor out, is there? So if I distribute on the top and subtract, I'm going to get 2x squared minus x squared is x squared. I'm going to get 6x minus, there's no x terms,
Negative 6x.
minus 6x, you're right. And then I'm going to get minus 2, right? Does that all look good?
Uh-huh.
And that's not factorable, but it is going to have zeros, isn't it?
Yeah.
Right? If we think about the discriminant, how do you know right away, can you look at this and say, okay, the discriminant's positive?
Because the middle term is bigger than.
Well, and in fact, because A is positive 1 and C is negative, right? So B squared minus 4AC, the minus 4AC is going to become positive then, right? Does that make sense? Okay, so you know right away, because of that, you know you're getting 2 real zeros of that. Okay, so we should expect to get critical numbers for our first derivative over x minus 3 squared. So, of course, this is kind of inconvenient, but at least we can do quadratic formula on this one. So if we find the zeros, f prime equals 0 when x squared minus 6x minus 2 equals 0. Let's just complete the square. That's easier, right? So if we add the 2 to this side, what do I have to add to both sides to complete the square?
3.
Negative 3 squared,
Yep.
right? So add 9. So I'm getting 11, and over here I'm getting x minus 3 squared, right? Okay? So then my answers are going to be x equals, if I square root both sides, I'm getting plus or minus the square root of 11, and then I'm going to have to add that 3 over. Right, so those are my 2 solutions. Okay, and remember if we get, remember talking about this in Algebra 2, if I get real zeros that are irrational, they always occur in conjugates of this form, right? In irrational conjugates. Remember talking about that? You're going to get a plus or minus b times the square root of c kind of a thing.
Yeah.
Okay. All right. So we got 2 of these guys. Let's go ahead and continue and get our second derivative. That's supposed to be a derivative, isn't it? Second derivative. So we'll go from here. Quotient rule.
You have your x minus 3 squared.
Okay. So we get x minus 3 squared d high. Okay, minus 2. Okay, now d low. That's going to be 2 times x minus 3.
Yeah,
Okay, good, good. All over
X minus 3.
to the fourth. And let's take a little shortcut here. We can see that I could factor out an x minus 3 and cancel it.
Yeah. Yep.
Okay, good. And then we're gonna get what on the top? So I'm gonna get, if I FOIL this out, we probably better go through this step by step. So I'm gonna get 2x squared minus 6x minus 6x plus 18. Oh boy, so here, oh no, so we just distribute a negative 2, that's easy. So minus 2x squared, that's good. Plus 12x, that's good. Plus 4, all over x minus 3 cubed. And so look, we get tons of good cancellation here. Those go, and I get 22 over x minus 3 cubed, right? So no zeros of the second derivative, right? So that's all good. So now when we make our table, what do we know? We only had, what was our, 3 was our asymptote, right? So x equals 3, our function was undefined. So we know this is a vertical asymptote. Okay, we had critical numbers at 3 plus or minus the square root of 11, so that's going to be like 6 point, what, like 2 or 3 or something, right? What is that real quick?
The plus is minus.
The plus would be
Plus is 6.3.
6.3. And then the minus is going to be something like negative 0.3-ish.
Yeah.
And so those are zeros of the first derivative. Okay, this is a pretty easy one to deal with, right? We just got to check the sign of the second derivative at those places. Well, the sign of the second derivative is really easy to check. It's positive on the top, and on the bottom, we're going to get a negative number cubed, which is negative here,
Yep.
right? So we're negative. Here we're going to get positive over a positive number cubed, so it's positive. And we got this thing, right? So we know then that, at least we got a lot of it. Where's 0? Down here. If we check these values in our original function, what are we going to get? So if I plug in negative 0.3, I'm getting something like, negative 0.7-ish probably, right? Something like that. Oh, yeah, about negative 0.7. So it's, we just get an idea. Okay, if we plug in 6.3, I'm getting something like, yeah, it'd be a little more than about 40, 43, just divided by, so what is that going to be? Somebody just, well, a little bigger.
No, wait, 14.
Yeah, like 40, something like that. We get the idea. We just were to basically put it on the graph, so all we're trying to get. So, something like this, we get a point. And that's pretty darn close to the origin, isn't it? And then here we get a point at, up here somewhere. Okay. And this is, what is this guy? We know we get a horizontal tangent, positive concavity, okay? And we get our asymptote right here, don't we? So then this one, I'm just gonna scoot that point down, because it's inconvenient. Say we put it here. It's just doing something like this, isn't it? Right? Okay, concavity's always up down here. Over on this side, it's gonna be negative concavity, so it's doing something like that, right? Pretty good? Okay, there's one other thing we can do though. What if we take the limit of this thing, at plus or minus infinity? Okay, what's gonna happen? What should we expect to happen here? It's a rational function. Top is a bigger order than the bottom.
So it goes
So it's not gonna have a horizontal asymptote, is it? Okay, but the top is 1 degree higher than the bottom.
to, so it has a slant.
So it has a slant asymptote, right? And so look, this is an easy, a really easy quotient to simplify because the bottom's linear.
And so you
Yeah, so I don't have to long divide this, right? I can use synthetic division to get this. So let's just review that real quick. Okay, so if we do synthetic division on this guy, we only have one to do, so we can just make a regular bracket. We don't need to nest it or anything. What goes out front? 3. What are my coefficients?
One,
0.
0, 2. Okay. So I get 1, 3, I add synthetically, right? 3, 9, 11. Okay. So then that means this equals what?
X plus 3
Plus.
11 over X minus 3.
Okay, so then if I want to do a limit of that, the limit of f of x as x approaches plus or minus infinity is the limit of x plus 3 plus 11 over x minus 3 as x approaches plus or minus infinity. Well, what's going to happen in that limit?
It'll go to
Well, sure, but what else happens? This term's gonna go to infinity, right? We get that, it's not gonna have a horizontal asymptote. That one stays at 3. What happens to that one? That one goes to 0, right? So the limit is x plus 3. Now, that is infinite, but it gives us the shape of the infinity, right? It gives the shape of the asymptote that guides our growth. It's x plus 3. So we get a slant asymptote at y equals x plus 3. So we can go back to our table then, and we could even do something like this. We could say, if we take our limit as x approaches infinity, it's x plus 3. So we get a slant asymptote there. And if we were to graph this thing, what would that look like? I didn't draw this very well,
It would
but
just-
that should have been, it would have followed this asymptote if I had been more careful in my drawing. It would have done something like that, right? Okay. Okay.